Okay, today we are testing. It's a two-sample dependent means t-test. Okay, so there's a lot in that. It's a two-sample test. We're going to use a t-distribution. It's a t-test. It's for the means. But what makes this lecture different from last lecture is very specific. It's that these samples are dependent samples, okay? Now, when we talk about dependent samples, it's usually a couple of possibilities, okay? One thing that is always representative of a dependent sample is if you do a before and after with the same group, okay? That's definitely dependent, and that happens a lot, okay? So one thing that we look for is a before and after. With the same sample. Okay, so that's dependent for sure. And other times we look for some sort of direct relationship or matched pairs. Okay, so this could be, we have a group of husbands and we look at them, and then in the next sample it's their wives or something like that. So you could have, husband, wife. So one sample is the group of the husbands, and then the wives are the other group, or any relationship like that. Twins. So we have one of the twins in one group and one of the twins in the other group. So some sort of matched pairs, okay, where there's a direct relationship between the sample. Okay. So when you're reading through a hypothesis test and you see a before and after situation, it should be relatively simple to say, okay, this is a dependent sample, okay, or specific match pairs, like we have twins or husband-wife or something like that, family relationship, okay? All right, so let's take a look at a couple of things. I have to define some new stuff for you. And the first thing that we want to look at is the hypothesis test is a bit different with the HO and the H1, okay? So instead of mu1 compared to mu2, we do what's called a mu sub d, okay? So it's mu with a little d next to it. So let's define what that stands for. This mu sub d is representative of the expected mean difference of the matched pairs, okay? So this represents the expected mean difference of the matched pairs. Okay? So, the expected mean difference of the matched pairs. The way that these are going to be set up, we only have three situations. One situation is mu sub d greater than or equal to 0 versus less than 0. Okay? Or you could have less than or equal to 0 versus greater than 0. Or you could have equal 0 versus not equal 0. Okay? So we're saying that the represented expected mean differences in this case is there's no difference versus there is a difference. Okay? And then in these two cases we're saying we're expecting one to be bigger than the other, or here we're expecting one to be less than the other in the difference. Okay? And I'll show you more specifically what I mean by that when we get to an actual problem. Okay? Now, the way we look at this difference thing, so we have this d, and primarily we're going to look at that in terms of before minus after. Okay, so if it's a before and after situation, we're going to find d to be the difference, before minus after, the actual difference. Okay? If it's a matched pairs, like husband-wife, then you just pick one to be 1 and pick the other one to be 2, and we'll just do it that way. But if it's specifically before minus after, let's keep this notation, b minus a, before minus after. Okay? here's what your t-test formula looks like. It's a test value, and it looks like this. T equals d bar minus mu sub d divided by s sub d divided by square root of n. And all of that's in the denominator, and all of that's in the numerator. Okay? And then, of course, if it's a t distribution, we have degrees of freedom. And the degrees of freedom on this problem is just n minus 1. Now, let's think about that for a second. How is it possible, if we have a two-sample test, that the degrees of freedom is just n minus 1?
Because they're dependent on each other.
Well, they're dependent, so what's true about those sample sizes? They're the same, right? If you have the same group before minus after, it's still the same number. So the degrees of freedom is just n minus 1. And then all of this stuff, we don't know anything, right? We don't know what d bar is. We don't know what s sub d is. We do know what n is. That's just a sample size, okay? And this hypothesized mu sub d, based on this hypothesis testing, was just going to be 0 primarily, all right? So the question is, how do I define this other stuff? So d bar, well, what is x bar? How do I get x bar?
Just the average.
It's the average, right? The mean of the x's. So if I wrote that statistically, symbolically, how would you get the x bar? What would you say? You'd add up the x's and divide by n, right? The amount. So the sum of the x's divided by n, okay? Well, d bar is the sum of the d's and then divide by n. Okay, so that should make sense, because x bar is the sum of the x's divided by n. D bar is the sum of the d's divided by n. But what's the d's again? It's the before minus afters. Okay, so that's what we're going to add up for each of them. Okay, and then if you guys go back into your notes from a long time ago, the standard deviation, we have that shortcut formula, and I'm just going to write that same formula, but this time we have it in terms of d instead of x. Okay, so my standard deviation formula in terms of d's is square roots, okay, and we have summation of the d squared minus summation of the d quantity squared over n, and all of that over n minus 1. And again, if you guys go back in your notes, this is the exact formula we did for our shortcut formula for standard deviation, and there's just x's here and here. Okay? And so you're going to have to go through that to get that value. So it's a little bit more work than we're used to in terms of we have to do a little bit of work to get these two pieces. Okay? So that is everything you need to know for this test. So now it's just a matter of, let's walk through a couple together and so you can see how it works. All right, let's do a couple examples. Example number 1. Okay, so let's read through this real fast. A program for reducing the number of days missed by food handlers in a certain restaurant chain was conducted. The owners hypothesized that after the program, their workers would miss fewer days of work. The table shows the number of days 10 workers missed per month before and after completing the program. Is there enough evidence to support, at alpha equals 0.05, that the food handlers missed fewer days after the program? Okay, so this is a before and after. So let me give you our findings. So we're looking at food handlers in a restaurant business, and this is how many days they missed before going through this program, okay? And this is how many days they missed after going through this program. So this first number is the first person. This is how many days that person missed before. This is how many days they missed after, okay? So the first person, it is 2, then 1. Then the next person goes from 3 to 4, then 6 to 3, 7, 8, 4, 3, 5, 3, 3, 1, and then we have 1, 0, 0, 1, and then 0, 0. So there's 10 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So we have how many days they missed before they did this program, and how many days they missed after the program. Okay, so the question was, at alpha equals 0.05, did the food handlers miss fewer days after the program? So at alpha equals 0.05, did they miss fewer days after the program? Okay? So if you saw this on a homework or a quiz or a test, it should be pretty obvious that this is today's material because it's a before and after situation. Okay, and this is the only problem that we've done with the before and after situation. Okay, so it's today's material. Test for dependent samples. So let's walk through some steps. Step 1, HOH1. And it's in terms of mu sub d. Okay, now this mu sub d is a little bit tricky because mu sub d, it's in reference to the before minus the after. Okay? Now the question here is they miss fewer days after the program. That's what we need to set up an inequality. Missing fewer days after the program. Okay, so if you miss fewer days after the program, then your before number should be higher than your after number. Does everybody agree with me? So your before minus your after is going to be positive because your before absences should be higher than your after absences, okay? So what's tricky about this is because I've trained you guys to think, oh, you see fewer or less than, that makes this a less than. But in this case, it's a greater than because it's specifically before minus after. Would have to be higher for you to miss fewer days. Isn't that weird? So it's a little tricky, so you have to be really careful with that. Okay? So again, we're saying this means missing less days after program. Okay? Because before minus after would have to be positive. Okay, so then this would be less than or equal to. All right, everyone okay so far? So it's a little bit tricky because of the language, but if you really think about it, the before would be more than the after, so that would be positive, so that would mean missing fewer days. Okay, let's go to our critical value. This is a, because this is greater than, this is a what-tailed test? Right-tailed test. So open up our t-distribution, we're going to go to a right-tailed test. The critical value, I gave you 0.05. The degrees of freedom on this problem is what? 9, right? There were 10 people in the sample, before and after, and then we just did one last, so it's 9. Okay, so look at your chart. One-tailed alpha 0.05, t-distribution, degrees of freedom 9. And let's see, what do you get there? 1.833? Does everybody agree with 1.833?
Yep.
Okay, and that's the end of step 2. So 2 steps out of 5 done already. Okay, before I jump into step 3, I got some things I have to do, right? So this is my test value. And again, this is t equals, and then if you look at it, it's d bar minus mu sub d divided by s sub d divided by square root of n. That one we have some work to do because we have to figure out d bar and we have to figure out s sub d. Okay? Okay, so I'm just going to bring a column over here and I'm going to call this the d column. Okay? And what did we say d was? Before minus after, right? So go through each one of these and just do before minus after. So I'll get you started. 2 minus 1 is 1, right? 3 minus 4 is negative 1. 6 minus 3 is 3. 7 minus 8 is also negative 1. 4 minus 3 is positive 1. 5 minus 3 is positive 2. 3 minus 1 is 2. And you have 1, negative 1, and 0. So your D column is just your before minus your after. Okay? If I sum up those numbers, what is that called? Sum of the d's. Okay? So if you sum up the d's, that's called the summation of the d's. So if you add those up, what do you get? 7? Does everybody get 7?
Yep.
Okay, great. All right, so d bar is sum of the d's, add up all your d's, which is 7, divided by what?
10.
10, right? D bar is the sum of the d's divided by n. So 7 out of 10, which is 0.7. Great. So I got one of the things that I need. D bar, again, if you look in your notes, it's the sum of the d's divided by n. Okay, and n is 10. Okay, the other thing I need is S sub d, the standard deviation of the d's. Okay, so I have to do another column. Let's do a d squared column. Okay, so take all of your d's, square them, and make a new column, and that'll be your d squared column. All of those, when you square them, should be positive. Okay, so make sure everything becomes positive when you square these numbers. So it's not too bad. 1 squared is 1. Negative 1 squared is also 1. 3 squared is 9. 1, 1, 4, 4, 1, 1, 0. And if I underline that and I add up all of those d squareds, that is going to be the summation of the d squareds. Okay? So go ahead and somebody add those up for me. 23? Okay, great. So the summation of the d squareds is 23. So circle that. We need that one, and we also need this one. And then I'm going to come over to the side of my paper, and I'm going to work out S sub d. Okay? S sub d is the square root of the summation of the d squared, which is 23. So that's my first number. Minus summation of the d, which is 7, quantity squared. So 7 squared over n, all over n minus 1. Okay, so I did that pretty quickly. Summation of the d squared minus summation of d, which is just 7, quantity squared, divided by 10, divided by 9. Okay? So, I'm sorry, was there a question? Yeah, because in this formula, it looks like it's a square root. This is summation of the d squared. This is summation of d in parentheses. And summation of d is 7. Okay. And then there's a square outside of that. Divided by n, divided by n. Okay, so let's just be careful here. So you have 49 over 10, which is what, 4.9? So we have 23 minus 4.9 divided by 9, and it's the square root of all of that. Okay, so I think that'll be the easiest way to plug it in. So 23 minus 4.9 divided by 10, square root of all of that. And double check that I get this right, and you guys let me know. $1.41813. Is that what you guys got? Yeah. 1.418136, something around there. So I'll just go 4 decimal places. 1.4181. 1.4181. Okay, so make sure you get something close to that. Okay, great. Now let's go to our test value. So we have d bar, which we did 0.7, minus the hypothesized mu sub d, which is 0. Our hypothesized difference is 0. S sub d, 1.4181. And square root of n, which is square root of 10. Okay, so you have 0.7 minus 0 divided by 1.4181 divided by square root of 10. So let's calculate that. 0.7 divided by okay, and I'm getting about 1.56095. Okay, so I'll go to 1.5610. So approximately 1.5610. All right, that is to the left of my critical value, 1.5610. It does not fall in the rejection region. So because it doesn't fall in the rejection region, I'm finally able to go to step 4, which is do not reject. Do not reject HO. Okay, so I come back to the top, I circle HO, and I'm going against this. So that was missing less days after the program. Okay, so the question was, at alpha equals 0.05, did the workers miss fewer days after the program? And we can't say that they did, okay? There's not sufficient or enough evidence to suggest that the program worked in the sense that they missed fewer days after, okay? So in your own words, no, they didn't. Okay. A lot of things are going on in this problem. Questions on this one? Okay, let's try another one. I'll get you started, and then you take off on it, and then we'll compare at the end. Okay? So let's try another one. So remember, there's some sort of direct relationship to make these dependent samples. Okay, here we go. A doctor is interested in determining whether a film about exercise will change 10 people's attitudes about exercise. The results of his questionnaire are shown below. A higher numerical value shows a more favorable attitude towards exercise. Is there enough evidence to support the claim at alpha equals 0.05 that there was a change in the attitude? Okay? So we have a before and after setup. Before these people watched a film about exercise, and after they watched a film about exercise. And the question is there a change in attitude? So change is the question. All right, so at alpha equals 0.05, is there a change in attitude? Okay, very similar to the last example in that we have 10 people, and we have a before score and then an after score. So I'm going to put up the before and after. And then you guys give it a shot. Okay, let me just do all the befores. So it's 12, 11, 14, 9, 8. 12, 11, 14, 9, 8. 6, 8, 5, 4, 7. 6, 8, 5, 4, 7. Those are all the before scores. The after scores are 13, 12, 10, 9. 13, 12, 10, and 9. 8, 8, 7, 6. 8, 8, 7, 6. And then the last two are 5, 5. Okay, and again, these are matched. So the first person's score was 12 before watching the film, and then their after score was 13. Okay? Let's all do HOH1 together. What does the question ask? Is there a change? What type of test is that? Two-tailed, right? Change in attitude. So if there's a change versus no change, that's equal versus not equal. Okay? So if you're saying not equal versus equal, so this is saying no change. This one's saying there's a change. Okay? Let's also do step 2 together. Let's make sure we both have the right critical values. And then I want you guys to try steps 3 through 5 by yourself. So we have two critical values here. The degrees of freedom is 9, just like the last problem. But alpha is 0.05 with 2 tails. Okay? So in your t-distribution, you look up 0.05 2 tails, which is the same as 0.025 and 1 tail. The degrees of freedom is 9, and what is the value there? 2.262. So you have positive 2.262, and you have negative 2.262. Okay? All right. Go ahead and give it a shot. You got to do your d column. You got to do your d squared column. You got to get the sum of the d's, the sum of the d squareds. So let me give you like 5 minutes, and then we'll compare answers. Okay, so hopefully everybody got a sum of d of 1, and then a sum of d squared of 29, okay? So then d bar should be 1 divided by 10, which is 0.10. The hypothesized mean difference should be 0, and the sum square root of d should be 29 minus 1 squared over 10 divided by 9, and in my calculator I got approximately 1.7920 for that. And then I just plugged it into the formula here. So we have d bar minus 0 divided by 1.7920 divided by square root of 10. And I got that came out to approximately 0.1765, which is somewhere close to the middle here. So it's not in the rejection region at all. So to finish up this problem, step 4, do not reject HO. And step 5, if I don't reject HO, I'm going with that there was no change in attitude. Okay? The before and after the expected difference was 0, so there's no change. Today's material is 2-sample dependent test for the means. Any questions on these problems? It should be obvious, because if it's before and after, it's very obvious, or it could say like, you know, husband and wife, or twin 1, twin 2, or something that's pretty obvious that they're matched pairs in some way. Okay?